Hi, my name is Marco Cavallo, and today I will present a personal work that started as a hobby a few years ago. And the topic revolves around doing computer graphics in more than three spatial dimensions, a field sometimes referred to as hypergraphics. As a quick introduction, let me start by clarifying what I mean by dimensions. In this paper, a dimension refers to an independent direction into which a geometrical space extends, not including time for now. If we consider a point and we extend it in one direction, we obtain a line. Then if we take this line and we extend it in an orthogonal dimension, we obtain a surface, or in this specific case, a square. And we can continue by extending the square into a three-dimensional cube. Along these lines, we can imagine a fourth dimension, which we'll call W, and extend the cube into the so-called tesseract or hypercube. Similarly to how the cube was bounded by 6 faces, the tesseract is bounded by 8 cubes, and we can see in this image how we can unfold its geometry. Before revealing the content of this presentation, let me try to add a little bit of context to explain how this concept of extra dimensions came to be, which is also one of the factors that motivated me throughout this work. So, the late 19th century saw an incredible scientific innovations, such as the identification of the electron, the studies on radioactivity, electromagnetic waves, and X-rays. And to be honest, I could really talk about this for hours. But what it is important to know is that these discoveries made us realize that human perception is limited, and that some supersensible reality that we cannot see or touch might actually exist. This occasionally allows science and supernatural theories to intersect with practices such as alchemy, and I'm not joking, spirit photography. And our world was seen as more of a boundary of some unperceivable higher dimensional reality. And a first geometrical example of this concept appeared in 1884 with the well-known novel Flatland, in which the author describes a set of strange phenomena experienced by the inhabitants of a 2D world, only to discover that these phenomena were simply manifestations of our 3D world. This also had a huge impact on art, with cubist and futurist artists such as Picasso and Boccioni showcasing in their work distortion, denial of three-dimensional perspective. But the concept of fourth dimension rapidly shifted towards the concept of time, with Einstein's relativity and Minkowski's space-time continuum. And for instance, in this period, we have the concept of block universe, where we as humans move across 3D time slices of a 4D hyperuniverse. But it was only towards the end of the 20th century that the emerging superstring theory predicted the existence of up to 11 spatial dimensions. And together with the hardware improvements in computer graphics, brought interest back to 4D spatial dimensions, with the first 4D simulations and the related artistic endeavors. In order to present 4D content to the human eye, in one way or another, we have to decrease its dimensionality, which unfortunately causes a loss of information. And in this sense, the focus of early visualization and graphics research has revolved around using rendering techniques to indicate 4D depth. At the same time, researchers try to better understand spatial relationships in higher dimensions, often using interactive manipulation as an exploration method. In parallel, some perceptual studies try to get a better idea of how the human brain could retain 4D information. In this work, rather than trying to improve on existing techniques, we try to shift the focus from the visualization of abstract shapes to a broader concept of hyperuniverse, where we do not just put our attention on a single geometry, but we try to build a world around it. Specifically, we try to generalize existing 3D technology as to interface 4D content. And we deal with problems related to creating content, 4D mechanics, and authoring worlds where both 3D and 4D elements can coexist. Finally, we aim at providing a comprehensive and self-contained baseline to help others continue on these topics, and in that sense, get ready to see a lot of content in this presentation. So all the graphical examples in this paper have been generated through our own very simple 4D engine, which we implemented as a Unity 3D plugin. And in the following slides, I will try to go over the basic concepts of rendering 4D content. And the goal here is not to present some fancy algorithm, but to give you an idea of how simple 4D notions can have a surprising effect on the viewer. The first concept is the one of projection, for which we support two methods. Cross-section takes the idea of slicing the 4D geometry, and in this example we consider the intersection of a hyperplane with a tesseract, and we can see how the intersection generates a triangle in each of the tesseract's bounding cubes, and we can then compose these triangles together as to form a 3D mesh. The second method is Frustum projection. That is a simple generalization of existing 3D projection and allows us to display 4D depth through the use of two distinct vanishing points. The geometry here is first projected into 3D space with a custom 4D projector, and then into screen space with the usual 3D camera projection. While cross-section is easier to compute and it's often found in interactive applications, Frustum projection is really mostly found in books about computer graphics. The next concept is 4D transformations. Let's start by imagining a 4D weapon shooting hypothetical 4D bullets with a spin that makes them sinusoidally move along the fourth dimension. As the bullet intersects the current cross-section, its geometry changes until the object exits the cross-section, with the interesting effect of making it invisible for a certain period of time. In Frustum projection, instead, the object simply becomes smaller as it gets further away from the viewer. Regarding rotations, we are used to think that the intersection of three axes generates three perpendicular planes. The reality in 4 dimensions is that 4 axes actually generate 6 orthogonal planes. And in this sense, we define 3 additional rotational variables, T, U, and V, to define 4D rotations. And in cross-section, a rotation around TUV has the effect of stretching the mesh in one direction. Whereas in Frustum projection, we have the effect of seeing the tesseract's bounding cubes turn inside out. Regarding scale, let's consider 3 objects and assign one of them a much higher hyperdepth than the others. As the viewer moves along W, the effect is that other objects will more rapidly exit the current cross-section, while the first one will remain unchanged. In this sense, we can see hyperdepth as a measure of how an object is resistant to change or how much it is persistent. As far as physics, the big question is whether 3D physics would generalize to 3D. And the answer is probably not, especially considering the implications of Gauss's law. However, for the sake of practicality, in this paper we assume 4D physics to be a simple generalization of 3D physics. And in this example we can achieve interactions such as a bullet first becoming invisible, hitting and revealing a hidden hyperplane, and then bouncing back on the ground until it rolls again out of the cross-section. In the next section, we are going to dive deeper into what it means to create a 4D universe, starting with its structure and then discussing about the ways to create and author its content. The first thing to consider is whether this 4D universe is Euclidean or has any compact dimensions. As an example of compactification, we can imagine a roller coaster winding its way through a 3D space, while its movement really can be described with a single independent variable. In a similar way, we can imagine a 2D wormhole or even parallel worlds, possibly connected by a bridge, where 2D beings do not realize living in a higher dimensional space. And in this sense, we do not necessarily need 4D content or even 4D movement to build a 4D universe. Another topic is the ability to move in higher dimensions. We definitely know humans cannot, at least voluntarily, move into the 4th dimension. So a person would not be able to escape from a 3D cage, for instance. According to physics, certain subatomic particles can, however, move in higher dimensions. And if for practicality we extend this concept to microscopic beings, we could explain something like a ghost easily entering and exiting the 3D cage. Finally, scientific experiments show that any higher dimension would have to be bound to an incredibly small extent, which is not really practical. But it is, however, worth considering limiting the extent of W mostly for performance and usability reasons. As a practical compromise, in this work we adopt a simple Euclidean 4D space where certain macroscopic beings can perform 4D movements under certain conditions, and where dimensions are theoretically unbounded. Once decided its structure, the next step is to figure out which content would populate such universe. The reality is that not much 4D content is available, and the easiest way to generate it is to take 3D perfect geometries and extend them like we did for the tesseract. And to be fair, we can achieve some decent effect even with simple geometries, like the animation of these 14 hyperspheres. However, this solution is too often abstract and lacks realism. The solution I personally like the most is analogy-based design, which tries to consider how objects and mechanics work in 2D and in 3D, and then tries to extend this concept to 4D. Unfortunately, this method is likely gonna fry your brain and is in general very time-consuming. Another idea is to try to build upon the promising research on 3D shape generation and use embeddings to generate hypothetical 4D entities. But this suffers from the lack of 4D data and with the lack of, I would say, behavioral semantics associated with 4D geometry. Our simple solution in this work is to extend existing 3D assets into 4D through lifting and tetrahedralization, with the benefit of obtaining familiar shapes, but the drawback of sacrificing the higher dimensional significance of such objects. Now that we have the content, we need to realize how to place it into space. And one technique is what we call 4D offsetting, that allows us to author content in normal 3D environments and then place it at different W coordinates. In this case, the viewer can move along the fourth dimension and transition between the different environments with a warping geometry effect based on their hyperdepths. And this allows us to achieve mechanics such as reaching objects hidden behind 3D obstacles. Something to consider while authoring is the amount of intrinsically 4D content that we want to introduce in the scene, which will highly impact the computational footprint of our application. Instead of extending all the 3D assets into 4D, our strategy in this work is to maintain a balance of 3D and 4D objects in the scene, where only the latter are affected by 4D movements, leaving 3D objects always visible. Another technique for transitioning between two apparently 3D environments is based on rotations. As an analogy, try to consider a 2D being able to move only left to right and upward downward. If we apply the rotation around the vertical axis, the entire world around him would change inexplicably, but we, as 3D beings, would be easily able to tell what happened from a 3D perspective. Similarly, we can imagine placing content in different 4D subspaces and use 4D rotations to transition between them, with the effect of warping the environment around the viewer. Now that we have outlined a number of ways to conceive a hypothetical 4D universe, it's time to settle on a subset of them and present our concrete use case, a video game we developed called Across Dimensions. The idea here was to create a non-didactic 4D application not too far from our common experience of 3D. The game has an FPS feel with puzzle and adventure elements, and the player can navigate a classic 3D world populated by 4D dimensional beings that hide in the environment and may suddenly appear to confront the player. The game currently runs on laptop with standard mouse and keyboard interactions, and in this early screenshot we can see, for instance, how a 3D header needs to be used to show the W offset of 4D beings with respect to the cross-section in which the player is currently situated, so that he can identify the position of invisible elements. On top of the standard 3D navigation, the player can accumulate a limited amount of crystal energy and use it to move along the W dimension, allowing him to pass the walls and reach otherwise inaccessible targets. The game also relies a lot on the concept of animating or morphing 4D geometries based on simple 4D auto translations. In certain instances, the player can perform direct manipulation using dedicated on-screen keys that can be used, for example, to mold an object into a bridge and use it to proceed beyond a steep drop-off. In this case, it's often hard to imagine a priori what shape a 4D object would assume, so we try to visualize floating previews of the effects of direct manipulation to help the user. As another example, a specific camera movement in frustum projection can be used to turn a barrier into a temple, into which the user can then enter and proceed in the game. A set of tools can also be used to bring nearby 4D objects to the current cross-section or reveal their geometry, or as we previously saw, they can be used to shoot bullets fluctuating along the 4 dimensions that can be used to hit invisible targets, such as 4-dimensional enemies that constantly try to escape the current cross-section as to avoid being noticed by the player. A key challenge that we tried to solve was trying to harness the potential of having a 4D camera with 2 completely different projection methods at our disposal. In the game, we applied cross-section projection by default due to its simplicity, so that 4D objects moving along the 4th dimension appear to gradually enter and exit the current cross-section hyperplane. In this case, the 4D projector shares the same XYZ components as the 3D camera, a setup that we call synced cameras. At any point in time, we can decide to keep the 4D camera fixed at its latest position, switch to frustum projection, and allow the user to move only the 3D camera, with the effect of generating 2 distinct vanishing points, an approach that we call detached cameras. When this happens, hyperdepth can be perceived by the viewer in the form of geometry transformations. The 3D mesh generated by projecting a 4D object depends on the pose of the 4D camera, and so our next idea here involved giving control over the 4D camera transform to the user, as to enable him to arbitrarily manipulate 4D content. As an example, the shape and trajectory of bullets can be dynamically altered just by moving the 4D camera, making it possible to hit targets around corners or to expand the bullet's collider in a specific direction. Unfortunately though, too many variables will have to be considered by the player in order to have full control of the camera, especially considering that this is just an overhead on top of the existing 3D mechanics. And so we decided to limit the movement of the 4D camera to an orbital trajectory, in which the player simply controls the initial focus point and the camera angle. And then we added some in-game visual aids to help him control these variables. Then when it's finally time to switch back to cross-section, we first gently interpolate the 4D camera pose as to match the 3D camera, and then we switch projection method as to make this transition as smooth as possible. While we didn't conduct a formal user study, we can discuss the challenges emerged during the development of Across Dimensions. Adding 4D elements to the game, for instance, enabled us to create new interactions, and gradually integrating them into an initial 3D environment definitely helped us with spatial orientation and storytelling. On the other hand, the effects of 4D transformations and camera projections are often hard to predict, making the design of new interactions too reliant on trial and error approaches, and consequently extremely time-consuming. In this sense, it might be worth exploring recommender systems to help the designer preview 4D behaviors and decide when it's convenient to apply them, as opposed to using more standard 3D techniques. In terms of performance, at least in our current implementation, we observed that every time an object goes through a 4D transformation, its projection into a 3D mesh needs to be recomputed, sometimes taking a big toll on the frame rate. And this affected the choice of 4D content in Across Dimensions, making us prioritize simpler geometry and having the player interact with only a few complex objects at a time, especially when in frustum projection mode. If you want to see some numbers, feel free to check the performance chart in our paper. Regarding user controls, we realized that the parametric explosion in camera parameters made it very cumbersome to create fast-paced applications that allow full control of both 3D and 4D cameras. Our suggestion here is to try to select only a subset of these parameters, and in this sense we actually believe that constraining the 4D camera movement could actually help the creation of more unique applications. Another thing worth exploring is the alternation of different projection methods for both performance and behavioral reasons, possibly dedicating some effort to creating visual helpers to guide the user, like we did with our 3D radar, for the manipulation previews, and the orbital camera visual aids. As a conclusion, we can say that despite science actually predicts the existence of higher dimensions, hypergraphics has historically been a very niche and difficult to approach research topic, in which interest has rarely stemmed from its potential usefulness, maybe except for a few applications to crystallography and particle physics. In this holistic work, we try to shift the focus as to conceive a broader concept of hyperuniverse, trying to encompass all major trade-offs and design considerations involved with extending common 3D technologies with 4D mechanics. Our use case in this sense served the purpose of showcasing how 3D and 4D elements can coexist and interact with each other in a concrete application. Here, our goal has been overall to make higher dimensions a little bit more accessible, hopefully inspiring other people to build new creative applications that go beyond our simple use case. I admit that it's been a very fun and different project for me, and I hope you guys enjoyed the presentation. Thanks for listening, and feel free to reach out to me for questions.